Good morning, all of you. Today I am going to make an audio recording for visual impaired students of Organic Chemistry book of Dr. J. M. Segal, Modern Book. Name of the chapter is Cycloalkanes. 4.12 Introduction. Cyclic aliphatic hydrocarbons or alicyclic hydrocarbons are hydrocarbons which contain closed chains or rings of carbon atoms and resemble open chain or aliphatic hydrocarbons in many respects. Like aliphatic hydrocarbons, alicyclic hydrocarbons may be saturated or unsaturated in nature. Saturated alicyclic hydrocarbons are generally known as cycloalkanes. They have the general formula CnH2n and are isomeric with alkenes. In this chapter, we shall discuss the chemistry of cycloalkanes. 4.13 Nomenclature of cycloalkanes. 4.13.1 Common names. Saturated alicyclic hydrocarbons contain a number of methylene groups joined together to form a ring. Therefore, they are known as polymethylenes in the common system. Accordingly, the individual members are named by prefixing the number of carbon atoms in the ring before the word methylene. For example, trimethylene, tetramethylene, hexamethylene. 4.13.2 IUPAC system. In the IUPAC system, the saturated alicyclic hydrocarbons are termed cycloalkanes. The individual members are named by adding the prefix cyclo to the name of corresponding state chain hydrocarbon having the same number of carbon atoms as the ring. For instance, cyclopropane, cyclobutane, cyclohexane. Quite often, alicyclic hydrocarbons are also represented by drawing simple geometrical figures such as a triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, and so on. The presence of carbon atom at each of the corners and hydrogen atom attached to carbon is taken for granted. For example, cyclopropane, cyclobutane, cyclopentane, cyclohexane. Nomenclature of substituted cycloalkanes. IUPAC name of substituted cycloalkanes are assigned by following the IUPAC rules, which the student has already studied. However, some important points are given below. First, for monosubstituted cycloalkanes, there is no need of numbering to indicate the position of the group. For example, methyl cyclohexane. Second, for cycloalkanes containing more than one substituent, the numbering of the carbon atom of the ring is done in such a way that the substituent get the lowest possible number. Their numbers are prefixed in alphabetical order along with their positions. Moreover, the substituent which comes first in alphabetical order is given the lowest possible number, provided it does not violate the lowest set of lock-in rule. For example, 1,3-dimethyl cyclopentane, 4-ethyl 1,2-dimethyl cyclohexane, 1-ethyl 2-methyl cyclopentane. Third, if the ring contains equal or more number of carbon atoms than the alkyl group attached to it, the compound is named as the derivative of cycloalkanes and the alkyl group is taken as the substituent as already shown above. Fourth, if the ring contains lesser number of carbon atoms than the alkyl group attached to it, or if more than one ring is attached to the single chain, the compound is named as derivative of alkane and the alicyclic ring is stated as the substituent. For example, 2-methyl 1-cyclopropylbutane, 1,3-dicyclohexylpropane. In addition to the above rules for cycloalkanes, some important points for naming cyclic compounds containing multiple bond and other functional group are given below. First, if the carbon chain attached to alicyclic ring contains a multiple bond or a functional group, the carbon chain is taken as the parent and the ring is treated as the substituent irrespective of the size of the ring. For example, 3-methyl 1-cyclobutyl but plus ene, 1-cyclohexyl but 2-ene 2-on. Second, if a compound contains an alicyclic ring directly attached to benzene ring, it is named as a derivative of benzene. For example, cyclohexyl benzene. 1 bracket 3 methyl cyclohexyl bracket close 4 nitrobenzene. Third, if the ring contains a multiple bond and the side chain contains a functional group, the ring is treated as substituent and compound is named as derivative of the chain containing the functional group. For example, 4-cyclohex 2 enyl butane 1 all. Fourth, if a functional group containing carbon is directly attached to an alicyclic ring, the carbon atom of this group is included in the suffix used for the group. For example, CHO group is represented by the suffix carbaldehyde, COOH by carboxylic acid, and CN by carbonitrile. Cyclopentane carbaldehyde, cyclohexane carboxylic acid. Synthesis of cycloalkanes and their derivatives. Only methods number 3, 5, and 7 are included in the syllabus. The important methods of synthesis of cycloalkanes and their derivatives are described below. Most of this method, may be noted, involves the conversion of some open chain compounds into a cyclic compound through the process of cyclization or ring closure. The cyclic compounds thus obtained may be a cycloalkane or its derivative. If required, the cycloalkane derivative is further subjected to suitable reactions to change it into the desired cycloalkane itself. First, addition of carbenes to alkenes. This method involves the addition of carbenes to alkenes to form cyclopropane derivatives. The reaction is also referred to as cycloaddition, since free carbenes are too reactive to be isolated. The reaction is actually carried out by using a carbene precursor that generates the carbene under suitable experimental conditions. For example, when treated with diazonium methane CH2N2 or ketene CH2 double bond carbon double bond oxygen in the presence of light, alkenes add on carbene to form cyclopropane derivatives. Alkene C double bond C plus CH2N2 diazomethane in presence of light gives substituent cyclopropane C single bond C and CH2 in cyclic structure plus N2. For instance, CH3CH double bond CH single bond CH3 2 butene plus CH2N2 gives 1,2-dimethyl cyclopropane. Second, Simons-Smith reaction. In this method, addition of carbene is carried out by treating the alkene with methylene iodide CH2I2 plus ZnCu coupled to get cyclopropane derivative. For example, alkene plus methylene iodide in presence of ZnCu gives substituent cyclopropane plus Zni2. Z and Cu couple required for the reaction is usually obtained by heating Zn dust with CuCl in ether in the presence of nitrogen. It is believed that methylene iodide and zinc react to form a carbene-like species called carbinode. CS2I2 plus ZnCu gives iodomethylene zinc iodide. The carbinode brings about the stereospecific addition of CH2 group directly to the alkene. Siemens-Smith's reactions gives better yield of cycloalkane that is obtained by the addition of free carbene to alkene. Third, photochemical 2 plus 2 cycloaddition reaction. The term cycloaddition denotes an addition reaction between two unsaturated molecules to form a cyclic product. During this reaction, new sigma bonds are formed at the cost of pi bonds of the reacting molecules. Individual reactions are designed by writing the number of pi electrons of each reactant in a square bracket. For example, a reaction between two alkenes molecules to form a cyclobutane ring by using 2 pi electrons of each molecule is referred to as 2 plus 2 cycloaddition. 2 plus 2 cycloaddition reactions can be carried out easily in the presence of light, but not under thermal conditions. Such reactions are termed as photochemical 2 plus 2 cycloaddition reaction. They take place by a concentrated mechanism involves cyclic transition state. The formation of substituted cyclobutane by photochemical 2 plus 2 cycloaddition of two alkene molecules may be represented in generally as follows. Alkenes give cyclotransition states, give substituent cyclobutane. For example, ethylenes give cyclobutane. Fourth, 4 plus 2 cycloaddition Diels-Alder reaction. 4 plus 2 cycloaddition reaction involves the addition of alkenes, that is 2 pi electrons, referred to as a dinomial diphile, and a conjugate diene, that is 4 electrons, to form 6 member systems. And constrain 2 plus 2 cycloadditions, this reactions take place radically under thermal conditions. For example, 1,3-butadiene plus ethene gives cyclohexane. If the diphenyl contains electrons attracting groups such as C double bond O, COOH, CnCl, the reactions take place extremely easily, sometimes even at room temperature. For example, 1,3-butadiene plus CH2 double bond CH single bond CHO gives 1,2,3,6 tetrahydrobenzyaldehyde. It is interesting to note that 2 plus 2 cycloaddition reactions take place radically, photochemically, but not thermally. On the other hand, 4 plus 2 cycloaddition reactions occur radically, thermally, but not photochemically. Fifth, dehalogenation of suitable dihalogen derivatives of alkenes. Freud method. On treatment of suitable alpha and omega dihalogen derivatives of alkanes, that is, dihalogen derivatives having the halogen atom attached to thermal carbon atom with sodium or zinc, they get dehalogenated to form cycloalkanes. For example, 1,3-dibron 1,3 dibromopropane plus Zn gives cyclopropane plus ZnBr2. Second, 1,4 dibromobutane plus Zn gives cyclobutane plus ZnBr2. The method may be regarded as an internal Wurtz reaction. However, this method gives good yield only in the preparation of cyclopropane. If the alpha omega dihalide contains more than 6 carbon atoms, intramolecular Wurtz reactions take place, giving rise to open chain alkanes. Sixth, Dickmann cyclization. When esters of certain carboxylic acids such as adipic acid and pimlic acid are treated with sodium or sodium ethoxide, they undergo intramolecular sign condensation to yield cyclic beta keto ester. The beta keto esters on hydrolysis and heating get decarboxylated to form cycloketones. The ketones are in turn subjected to Clemson reduction to get cyclic alkenes. For instance, adipic ester in presence of NaCO C2H5OH gives 2-carbo-betaethoxycyclopentanone gives in presence of H2 gives 2-carboxylic cyclopentanone. In presence of CO2, uh, heat minus CO2 gives cyclopentanone. In presence of ZnHg HCl gives cyclopentane. Ditchman method is most suited to the preparation of 5 and 6 membered ring. Pyrosis of calcium or barium salts of dicarboxylic acid. Vincennes method. When the calcium or barium salts of certain dicarboxylic acid are heated strongly, they yield a cyclic ketone. The ketone thus formed is converted into cycloalkane through Clemson reduction as illustrated below. Calcium adipate in presence of heat, cyclopentanone in presence of Zn, Hg, HCl, cyclopentane. In keeping with blank rule, this method is used for the preparation of 5 and 6 member ring ketone. Blank rule. This rule was formulated by Blank on the basis of experimental observations of the ease of formation of cyclic anhydrides and ketones by distillation of dicarboxylic acid according to relative positions of two carboxylic groups. According to the rule, distillation of 1,4 and 1,5 dicarboxylic acids gives rise to cyclic anhydrides, while 1,6 and 1,7 dicarboxylic acids yields ketone. 1,8 and higher dicarboxylic acid remain unaffected. Blank's rules can be used for determining the size of the ring as well as the chain length of the dicarboxylic acid. For this purpose, a double bond is introduced by suitable method in the given compound, whose ring size is to be determined. The unsaturated compounds thus obtained is subjected to oxidate cleavage with KMnO4 to get a dicarboxylic acid. This acid is heated with acetic anhydride and distilled. If a cyclic anhydride is obtained as the product, the acid is either 1,4 or 1,5 in nature. If a cyclic ketone is formed, the acid as 1,6 or 1,7. If there is no change, the acid is 1,8 or higher. The structure of the acid is turned reveals the size of the ring. 8th, Thorpe-Ziegler reaction. On heating in the presence of lithium diethylamide C2H5 bracket twice N minus Li positive and alpha beta dinitrile, that is, a dinitrile in which nitrile groups are attached to terminal carbon atom, undergoes intramolecular condensation to form a cyclic aminonitriles. This is changed into cycloalkanes as is illustrated below. Alpha omega dinitriles in presence of C2H5 twice N negative Li positive gives aminonitriles in presence of water gives keto acid, in presence of heat gives ketone, in presence of ZnHg HCl gives cycloalkanes. In the first step in the reaction involving cyclizations take place only at very high distillation. It is referred to as Ziegler high dilution technique. Thorpe-Ziegler reaction is particularly suitable for the preparation of higher ring compounds. Ninth, Demjanov rearrangement. This reaction provides a method of expanding and contracting alicyclic ring system through the formation of carbocations. The carbocations themselves are obtained by the deamination of alicyclic amines by treating with the nitrous acid. Once formed, the carbocation undergoes its characteristics reaction, that is, first addition of nucleophile, second elimination of a proton, third rearrangement to a more suitable carbocation. As a result, different products are formed, including ring expansion or ring contraction products as illustrated below. Ring expansion. When cyclobutyl methyl amine first is treated with nitrous acid, we get four products: cyclobutyl carbinol third and methylene cyclobutane second are formed without involving any ring expansion. At the same time, cyclopentanol fourth and cyclopentene fifth are formed by ring expansion as shown below. First, in presence of HNO2 gives carbocation, and then in presence of H positives gives second, and in presence of H2O gives third. Ring contraction. When cyclobutamine 6 is treated with nitrous acid, cyclobutanol 8th is formed without any ring contraction. At the same time, cyclopropyl carbinol 8 is formed by ring contraction. 6th, in presence of HNO2 gives carbocation, then in presence of water gives 7th, then in presence of Dimjano rearrangement, at last it gives ring contraction. It may be noted that when the carbocation initially formed carries the positive charge on the alicyclic carbon, it leads to ring contraction. On the other hand, when the initial formed carbocation carries the positive charge on carbon alpha to the alicyclic ring expansion takes place. 10th, hydrogenation of aromatic compounds. Cyclohexane and its derivatives can be prepared by the hydrogenation of benzene and its derivative. For example, benzene plus 3H2 in presence of nickel 473 Kelvin gives cyclohexane. 11th, condensation of suitable dihalides with malonic ester or acetoacetate ester followed by hydrolysis and decarboxylation. In the presence of sodium methoxide, active methylene compounds such as malonic ester and acetic ester condense with suitable dihalides to form cyclic diesters. These are hydrolysis and decarbonylation lead cycloalkanes, for instance. Ethylene dibromide plus malonic ester plus 2C2H5ONA gives cyclopropane dicarboxylic ester plus 2C2H5OH plus 2NaBr. Then in presence of water gives cyclopropane dicarboxylic acid. Then in presence of heat gives monocarboxylic acid. Cyclopropane monocarboxylic acid is then converted into cyclopropane through a sequence of reactions. It may be noted that this acid cannot be directly decarboxylated by heating, as it leads to cleavage of the ring. Acetic ester may be used in place of malonic ester in this reaction. For example, the ketone obtained above is suitably treated to get the corresponding hydrocarbons. 4.15 Physical properties. First, in their physical properties, cycloalkanes resemble the corresponding open chain compounds, although they have a somewhat higher boiling point and densities. For instance, the first two members of cycloalkanes, that is cyclopropane and cyclobutane, are gases, while higher members are liquids. Second, they are non-polar in nature and as such insoluble in water but soluble in organic solvents. Some of them, such as cyclohexane, are good solvent themselves. 4.16 Chemical properties. The general chemical behavior of cycloalkanes is similar to that of corresponding open chain hydrocarbons. Like alkanes, cycloalkanes also contain only carbon-carbon and carbon-hydrogen sigma bond and are therefore quite inert towards chemical reagents and undergo only a few substitution reactions. It must be emphasized, however, the cyclopropane and cyclobutane differ considerably from their higher homologs. This is because the cyclopropane or cyclobutane rings are not very stable and have a tendency to open up and form addition products, as explained in 4.17.1. As such, they resemble alkenes in undergoing some addition reactions, but they are less reactive than corresponding alkenes. A few reactions of cycloalkanes are described below. First, reaction with halogens. Generally speaking, cycloalkanes undergo free radical substitution with halogens at high temperature or in the presence of light. For example, cyclohexane plus Br2 in presence of light gives bromocyclohexane. Cyclopropane plus Cl2 in presence of light gives chlorocyclopropane. In case of cyclopropane, however, bromine and chlorine break the ring system in the presence of FeBr3 or FeCl3 and high temperature and yield open chain addition products. For example, cyclopropane plus Br2 in presence of FeBr3 gives 1,3-dibromopropane. Second, reaction with halogen acid. In general, cycloalkenes do not react with halogen acids. However, cyclopropane adds on halogen acid to form open chain halides. Cyclopropane plus Hi gives N-propyl iodide. Cyclopropane plus HBr gives N-propyl bromide. Cyclohexanes plus Hi do not react. No reaction. Third, addition of water. When heat with concentrated H2SO4, cyclopropane but not other cycloalkanes add on water to form an alcohol. Cyclopropane plus water in presence of H2SO4 gives N-propyl alcohol. Fourth, reaction with hydrogen. When heated with hydrogen in presence of nickel, cyclopropane and cyclobutane form open chain addition products with higher cycloalkanes do not react. Reaction of cyclobutane take place at much higher temperature than required in case of cyclopropane. Cyclopropane plus H2 in presence of nickel at the temperature 353 to 373 Kelvin gives N-propane. Cyclobutane plus H2 at high temperature gives butane. Cyclohexane plus H2 no reaction. It may be noted that of the cycloalkane, cyclopropane is the most reactive since it undergoes many addition reactions accompanied by ring cleavage. Next comes cyclobutane, which undergoes addition of hydrogen, while the rest of cycloalkanes do not form addition products. Relative stabilities of cycloalkanes, Beer-Stein theory. During the earliest stages of these studies, cycloalkanes containing up to only 6 carbon atom rings could be prepared in the laboratory, and the rings containing 7 or more carbon atoms were unknown. It was also observed quite early that, like open chain alkanes, cyclopentane and cyclohexanes are quite stable and do not undergo addition reaction. On the other hand, cyclopropane and cyclobutane were found to be relatively much less stable and capable of undergoing even addition reactions through ring cleavage. The difference in the relative stabilities of different cycloalkanes was initially explained in terms of Beer-Stein theory as discussed below. 4.17.1 Beer-Stein theory. According to tetrahedral concept of carbon, a carbon atom bonded to 4 other atoms lies at the center of tetrahedron, and the angle between any two bonds is 109 degree 28 minute. Adolf von Baer 1885 argued that any departure from this position leads to a strain in the molecule, as a result of which the stability of the molecule decreases. On the basis, Baer proposed a theory now known as Beer-Stein theory. The most important points of this theory are: first, the carbon atoms contain the ring in the same plane. Consequently, the bond angle between the adjacent carbon atoms of the ring no longer remain 109 degree 28 minute, which is the normal bond angle of the tetrahedral carbon. On the other hand, different rings have different values of this angle. For instance, the cyclopropane ring is a triangle having a carbon angle of only 60 degree. Second, any deviation, positive or negative, from the normal tetrahedral bond angle of 109 degree 28 minute during the formation of a ring produce an internal strain in the resultant molecule, which make the molecule unstable. Positive deviations means that the angle is compressed, while negative deviations means that the angle gets expanded. Third, the greater the deviation from the normal angle, the greater is the strain, and therefore the lesser is the stability. It may be noted, however, that the angle of deviations make no difference. Fourth, the more the stability of a ring system, the more easily it's formed. where calculated the deviation from normal angle or what may be called angle strain involved in the formation of cycloalkanes of various ring sizes. For example, the carbon-carbon-carbon angle of cyclopropane ring is 60 degree since each carbon atom occupies a corner of an equatorial triangle. This means that the angle strain in cyclopropane would be 1 by 2 of 109 degree 28 second minus 60 degree is equal to 24 degree 44 minute. Similarly, the carbon-carbon-carbon angle in cyclobutane is 90 degree as each carbon atom is situated at the corners of a square. As such, the angle strain in cyclobutane is 1 by 2 109 degree 28 minute minus 90 degree or 9 degree 44 minute. The angle strain in cycloalkanes of various ring sizes are summed up in table 4.1. Table 4.1 Angle strains in various cycloalkanes. Compound carbon-carbon-carbon angle strain. Cyclopropane C3H6 60 degree 24 degree 44 minute. Cyclobutane C4H8 90 degree plus 9 degree 44 minute. Cyclopentane C5H10 108 degree plus 0 degree 44 minute. Cyclohexane C6H12 120 degree is minus 5 degree 16 minute. Cyclopentane C7H14 128 degree 34 minute minus 9 degree 33 minute. Cyclooctane C8H16 135 degree minus 12 degree 46 minute. Evidence in favor of Bayes strain theory. First, it is obvious from the bond angles that the magnitude of strain goes on decreasing as we proceed from cyclopropane to cyclopentane. Hence, ease of formation and stability should show a corresponding increase. This is actually found to be so. The ease of formation and stability of cyclohexane could also be justified in view of the small angle strain in its case. The fact that cycloalkanes having 7 or more carbon atoms were not known to exist at the time of Bayer was attributed to the increasingly large strain in the formation of higher rings. Second, Bayes strain theory could also account for the great reactivity of the ethylic bond. The double bond was treated as two-membered ring in which the angle strain is 54 degree 44 minute. This large strain seemed to be responsible for the reactivity of double bond. Limitations of Bayes strain theory. Bayes theory failed to explain the following. First, ease of formation of ethylic bond. The ethylenic bond can be formed readily in spite of having such a large angle strain. Second, stability of cyclohexane and higher cycloalkanes. Heat of combustion of cycloalkanes. Bayes strain theory failed to explain the stability of cyclohexane and higher alkanes as discussed below. Cyclohexane and higher cycloalkanes, many of which were prepared after Bayes theory has been proposed, are found to be nearly as stable as cyclopentane as shown by their heats of combustion. The heats of combustion per methylene group CH2 of various cycloalkanes as given in table 4.2. Size of the ring. Heat of combustion per CH2 group kg mole per second per. Size of the ring. Heat of combustion per CH2 group 697 966 669.4 4 686 10 663.6 5 664 11 662.7 6 658.5 12 659.3 7 662.3 13 660.2 8 663.6 14 658.5 Heat of combustion per CH2 group of open chain alkanes equal to 658.5 kilo per mole. The heat of combustion per CH2 group gives a fair idea of the relative stabilities of cycloalkanes, since each CH2 group yields only carbon dioxide and water on combustion. If the heat of combustion is large, the compound contains more energy and is therefore less stable, and vice versa. It is immediately apparent from table 4.2 that as compared to open chain alkanes, cyclopropane and cyclobutane gives out nearly 38 and 28 kilojoule more energy per CH2 group. This means that there are relative less stability effect, which is in agreement with base chain theory. However, the heats of combustion per CH2 group of cyclopentane, cyclohexane and higher cycloalkanes differ only very slightly from that of open chain alkanes. This implies that cyclopentane and higher ring alkanes are nearly as stable as open chain alkanes. This obviously goes against Bayes' theory, according to which cycloalkanes having more than 5 carbon atom rings should be increasingly less stable due to increasing deviation from the normal tetrahedral angle. 4.18 Saxe-Mohr theory of stainless rings, to explain as to why cycloalkanes having rings of 6 or more carbon atoms are most as stable as cyclopentane. Saxe 1890 put forth a theory of stainless ring for higher rings compounds. According to him, carbon atom consisting the ring lies in the same plane only up to 5-membered ring, while the carbon atom in 6-membered and higher rings do not lie in the same plane. Since the carbon atoms in 6-membered ring and higher rings lies in different planes, the normal tetrahedral angle remains unaltered. As such, there is no angle strained in bigger rings, and that is why they are stable. For instance, such same proposed the existence of two types of multi-planar or puckered stained rings known as chair and boat form for cyclohexane. Both this form and are free from angle strain and can be interconverted just by rotating around single bonds. Thus, they merely represent two conformations of cyclohexane and cannot be isolated separately. Chair form, boat form. Figure 4.5 Stainless ring of cyclohexane. Similarly, 7-membered and higher rings are stainless in nature. Such a theory of stainless ring was further supported and elaborated by Mohr, 1918, to cover the compounds containing two rings fused together. Difficulty encountered in the synthesis of large-membered ring. It may be interesting to know as to why bigger rings are rather difficult to synthesize, even though there is no angle strain in them. This is primarily due to the fact that two ends of the chain of atoms must come closer together for ring closure to take place through interaction between the groups present at the two ends. If the chain undergoing ring closure is very long, there are reactively lesser chances of the two ends coming close enough for the ring to be formed. On the other hand, what may happen if the end of one chain may interact with the end of a different chain, leading to the formation of an entirely different compound. This difficulty is now being overcome by carrying out a ring closure reaction in highly dilute solutions. Under these conditions, collision between different chains are minimized and the ring closure takes place as the main reaction, although at a very low rate, but only the rings are formed. They are quite stable. 4.19 Bent or banana bonds in cyclopropane orbital picture of angle strain. According to orbital concept of covalency, a covalent bond can be formed between two atoms only if these atoms are oriented in such a way that the orbitals can overlap each other. It may also be recalled that the greater the overlapping of atomic orbitals, the stronger the bond formed. Now, the carbon atoms of cycloalkanes are in a state of sp3 hybridization, and formation of covalent bond between two such atoms involves the overlap of an sp3 orbital of one carbon with a similar orbital of another. For maximum overlap, the bonding should take place in such a way that bonding orbitals point directly towards each other. Consequently, when carbon is bonded to two other carbon atoms, the carbon-carbon-carbon bond angles should be 109 degree 28 minute. But in cyclopropane, the carbon-carbon-carbon bond angle is only 60 degree. This means that in cyclopropane, the bonding orbitals are not pointing directly towards each other along a straight line. As a result, the overlap of these orbitals take place to a very small extent, and bonds formed are described as bent bonds. These bonds are much weaker than the normal carbon-carbon bonds. Consequently, the cyclopropane molecules is quite unstable or strained and reactive in nature. A. B. Figure 4.6 A. Maximum overlap of sp3 orbitals of carbon in open chain or large ring compounds. B. Poor overlap of sp3 orbitals of carbon in cyclopropane ring. Only the orbitals concentrate in bond formation shown. In cyclobutane, carbon-carbon-carbon angle equal to 90 degree, the overlap is relatively more effective than in cyclopropane. As such, cyclobutane is relatively more stable. Thank you.